Good afternoon, good morning everyone from wherever we are across the globe, and thank you for joining the Clarke Energy and Association for Decentralised Energy's webinar on understanding the performance and sort of best practices with regards to combined heat and power technology. We'll have three speakers today: myself, Adam Wray-Summerson, Major Projects Specialist for Clarke Energy. We will also have David Burke, who is the Service Director for Clarke Energy, and Jonathan Graham, the Head of Policy for the Association of Decentralised Energy. And what we would like to do today really is take you through a whistle-stop tour, given that we haven't much time, but essentially an overview of gas engine technology, how we would look at a project in regards to feasibility and design, engine control systems, through life maintenance, and then look at some case studies before we discuss some of the existing policy and industry regulation that is pertinent to us, particularly in the UK. I would like to start just by very quickly introducing Clarke Energy. We were acquired by Kohler Company in January of this year, but Clarke Energy as an organisation has existed since the late 80s, where we operated primarily in the diesel and offshore engine service industries. It was in the mid-90s that we became involved with gas engines and were approached by Jenbacher GmbH, as they were prior to General Electric's acquisition, for the distributorship of the UK gas engine market. That relationship has since blossomed and grown, and we now represent GE Jenbacher in 20 territories worldwide, with an installed gas engine base of some 5.4 gigawatts across all of those territories, continuing to see annual growth, now 1,100 employees worldwide, and various ISO accreditation for quality, environment, and health and safety. Heat and power, if we were to enter a question into Google as to what combined heat and power is, essentially we would get this response: CHP is a high efficiency technology for generating power, usually in the form of electricity and heat on-site from a single fuel source. What do we mean by that? Essentially, applying a fuel source to a reciprocating gas engine, the rotational moment of that engine drives a generator to produce electricity that can be used on-site or exported to a local grid. As a byproduct of the electrical generation, what the engine also does is generate heat from a number of sources, and that heat can be utilised through combined heat and power in a number of ways, whether that's for space heating, for process heating, for cleaning or sterilisation activities, or a wide variety of different applications. The primary heat sources from the unit, heat is picked up from the lubricating oil circuit, the engine jacket cooling circuit, and the intercooler, which is sometimes referred to as the turbocharger aftercooler circuit. That's what we call the low-grade heat available from the unit. You also have a higher grade of heat available from the engine exhaust, which could be directly linked into that hot water system, or could be used to raise steam or directly fired exhaust. There are a multitude of excuse me. So looking at sort of various applications and how one might integrate engines or a number of engines into a system, we could look at integrating all of the hot water into a single circuit, and that may be used to deliver heat to a heat consumer. What we might also use are peaking boilers, so retained boiler plant on site as part of the CHP installation, such that sort of the highest levels of peak demand might be satisfied from a natural gas fired or an alternative fueled boiler plant. What you may also want to include within the bounds of the scheme might be a heat vessel or heat buffer, and that may be beneficial where the economic balance for operating the unit varies. And what I mean by that is actually it might be more economically viable to generate electricity during daylight hours, but actually heat recovery may not be as pertinent during those times. So by incorporating a thermal store buffer vessel into the circuit, that enables us to do is essentially deploy that heat as and when it's required more effectively. Taking that a step further, what we might also consider integrating into the system might be technology called absorption chilling. And an absorption chiller uses some form of cooling medium, quite often lithium bromide, to utilize hot water off the engine, say at 90 degrees Celsius, to generate chilled water in the region of 6 degrees Celsius flow, 12 degrees Celsius return. And this might be particularly beneficial in hotter countries where air conditioning of a factory or of a plant is required. It may also be beneficial in applications such as data centers, where there is a higher cooling load, cooling demand, than there might be heating demand. Moving on from that, the other potential resource that can be recovered from the engine may be carbon dioxide, CO2. And we can utilize our exhaust gases and clean and scrub those exhaust gases to recover, up to food grade quality carbon dioxide, which might be used in a greenhouse for helping boost crop yield of tomatoes or peppers, for example. Equally, you may use that in a food and drinks application in order to apply the fizz to carbonated drinks. So all in all, we have a number of different considerations to be made with regards to the electricity generated, with regards to the heat available from the engine, with regard to what we can do on the exhaust system. And all in all, what this enables us to do is produce power and heat on site, maybe in the region of 90 to 95% total efficiency of the project. Why might we actually look at doing this? Well, primarily there are a number of, there may be a number of reasons for looking at a CHP scheme, but in most applications across the globe, certainly those are driven by driving energy savings and cost savings in particular. And the way that this is defined is using the spark spread. So on the left-hand side of the graph, what you can see here are essentially the costs of generating heat on site, normally in the form of boiler, and the cost of buying in electricity, normally from the local network or from diesel generation, for example. On the right-hand side, what we have is the relative cost and associated saving of generating power and heat from the CHP. So on the right-hand side, what we have is the CHP fuel cost, so the fuel input to that unit, which will have a variation in price depending on the cost of gas. We then also have the cost of maintaining the equipment, and the difference between the left-hand side and the right-hand side is then the savings represented in yellow there at the top of the graph. And depending on the scheme, depending on the economics, depending on the territory, those cost savings might be somewhere in the region of between 20 and 50%, depending on where we are in the world. So it's quite substantial savings that can be achieved from a CHP scheme. Equally, as a benefit of high efficiency generation on site, we also have the potential of offsetting carbon dioxide emissions into the atmosphere in respect to the carbon associated with generating electricity on the grid and having to transport and distribute that power to your site, and the carbon associated with generating that heat that you provided previously. So in terms of best practice at looking at project development, what is critical to the success of any CHP scheme is a thorough understanding not only of how to deliver and install a project, but actually how to assess a project in the first instance. So what we would do, on receipt of an inquiry, is assign a complete bid team to that proposal who would look at the detailed feasibility analysis, and I'll discuss that in some more detail shortly. That feasibility analysis then provides us with the baseline for a design solution. We'll then build up that design solution, obviously during a period of time of contractual negotiation with the customer before any project award is made. And then the kind of the end-to-end service offering that Clarke Energy can provide enables us from that point of receipt of inquiry right through to the project delivery and execution phase of the project, including all of the required health and safety legislation, hazardous substances and all those kind of assessments that need to be made prior to commencement of works on site, right through to delivery of equipment, full mechanical and electrical integration onto a site, filling of systems ahead of commissioning, performance testing, and then the ongoing service and maintenance, which David will discuss in more detail later on. So the critical stages at the start of the project are feasibility analysis. And this is essential for all sites really to ascertain the benefit of a potential combined heat and power facility. And what I might add is it is important to analyse both the electrical consumption on site, thermal consumption on site as they are today, as well as integrating any kind of forecast for how those site loads may develop or change throughout the course of a project. What also needs to be analysed at the feasibility stage is actually the ability of your potential supplier to deliver the project. So even at this very early stage, it's important to consider reference installations, to consider product experience, technology experience, and things like that. And then fundamentally, you then have to assess the full life capability of that unit and of that potential supplier. So it's fine saying that a 1 megawatt natural gas CHP solution may work for a particular application, but then actually understanding how that unit will be able to operate through 15 through 20 years is critical to actually being able to achieve the levels of savings that are being promised at the early stages of the project. How might we actually then look at sizing a unit? What the graph here tries to show us is a typical heating profile throughout the course of a year. So January through to December on the x-axis at the bottom, and then the curve, obviously heating requirements tend to be higher during the winter months than they are in the summer months. Now, if we were to look at a potentially large engine that satisfies all of those peaks in demand, that could possibly give us the greatest level of savings. However, during the summer months, there may well be a need for rejecting some or all of the heat, which may impact some of our CHP quality assurance scores, as Jonathan is going to discuss later. But equally, that might be acceptable from an economic standpoint. If we were to reduce the size of the engine and potentially offer something a lot smaller, this is probably the safer option where you will get the greatest amount of running hours out of the engine. However, you might not necessarily realise the greatest level of savings that are potential for your site. So what we need to analyse is that middle section, the kind of sensitive analysis area of the graph, where actually it might be beneficial to reject some heat a proportion of the time, or it might be beneficial to back off the engine from full load operation for short periods of time. And in order for us to be able to do this analysis as accurately as possible, what is essential is to look at and understand to the highest level of sensitivity the electrical and thermal demands on site, as I previously mentioned. And typically what we require for that would be half-hourly electrical consumption data, or in some instances 15-minute electrical consumption data, and then the corresponding thermal data for site. And invariably, people don't meter how they use their heat as well as they meter how they use their electricity. And this can potentially cause an issue in trying to determine the best sizing for the unit. But what we would always like to do is analyse as closely as we can. So perhaps understanding the thermal consumption in terms of gas consumption to the boilers, or fuel to the boilers that's providing you current heat, or if it's a site with that's running electric chillers, then understanding the chiller loads and the proportion of electricity that is currently being used on site to generate that chilled load. Understanding all of these sort of elements will then help enable us to accurately size a unit specific to that particular project. Moving on from that initial feasibility phase then, what becomes equally important are the complete design considerations. Clearly, it's not just the engine and generator that will provide the levels of savings that have been advised during the feasibility stage, and it's important to understand the complete balance of plant. So with regards to layout, what we're talking about is integration into an existing facility. It may be a Victorian boiler house in central London, which may have its own kind of perks, nuances and difficulties in terms of how we would deliver the project. It might equally be a greenfield site in Africa where we haven't got concerns with regards to layout or clashes with other equipment. Understanding the balance of plant then becomes critical, so in terms of the ventilation systems, the exhaust silencing, fuel delivery, electrical integration, mechanical integration, thermal circuitry integration, thermal balancing with the site. All of these things need to be carefully considered at the design stage in order to ensure that upon completion of the project, the performance characteristics advised will actually be achieved. What is also important to consider is the integration with existing services. How will integration of these units affect system resilience? Are there any requirements for planning? Is it a change of use, or is it a new planning application that is required? And all of this the planning element can be delivered as part of our design package. So your submission to the local planning authorities, we can assist with that with regards to layouts and design. Then, when you're connecting to the electricity grid, certainly in the UK, a grid connection application needs to be made, which enables the network provider to ascertain fault level currents, to ascertain whether their existing infrastructure may require upgrading or is suitable for connection of the generation plant. Also, very critical to the overall design of the scheme, and this is becoming more prevalent in the United Kingdom as well as across Europe, and certainly in the United States as well, is dispersion modelling. So actually analysing the exhaust emissions from the units, or a collection of exhausts from the units, and how that affects local NOx emissions, nitrous oxide emissions, and carbon emissions and things like that. So all of this needs to be considered during the design phase to ensure that an accurate project can be delivered. Moving on then to the gas engine concept, and trying to, we almost doing, coming back on ourselves essentially. But what we're considering is a conversion of chemical energy into kinetic energy to provide a rotary movement. In our case, that rotary movement drives a generator for generation of electricity. And there are some fundamental differences between a bespoke gas engine and a diesel engine that's been, or a diesel-derived engine that has been converted for use on gaseous fuels. Diesel, by nature of the type of fuel that it is, burns wet as it's a liquid and relatively cool, whereas a gas engine burns very, very hot and very, very dry. So in terms of the thermodynamic effects within the combustion chamber, in terms of the metallurgy of the equipment that's being supplied, there are some interesting considerations that need to be made when looking at the gas engine technology. And always going back to school for some of us, this image basically shows us the 4 stages that are considered during combustion. So this basically representing the Otto Cycle, so-called after Nicholas Otto, who developed the principle in the late 1800s. So essentially we have 4 elements within the combustion cycle. So on the leftmost, it's not actually in order, is the power stroke, the bang, essentially, where we are introducing a spark to a compressed mixture of air and fuel, which drives the piston down in the cylinder liner. The second image then is the actual exhaust stroke. So with the piston moving back up within the cylinder, the exhaust valve is open, the inlet valve is closed, and this is exhausting the spent mixture, the combusted mixture, into the engine exhaust. The third element of the image then is the intake stroke. So the inlet valve is open, the exhaust valve is closed, and we're drawing or inducing into the combustion chamber a mix of air and fuel. And then the compression stroke, which is the rightmost picture, is where both the inlet and exhaust valve are closed, and we're compressing that gas-air mixture prior to bang. So essentially, suck, squeeze, bang, blow is the principle, or induction, compression, power, and exhaust, if you want to be a little bit more technical. Moving along from the original Otto principle then, a lot of engine manufacturers have developed their timing cycles in order to try and drive lower emissions, drive higher efficiencies. The GE Embacher product utilizes Miller timing, so-called after the chap that kind of developed this principle. And there are 2 concepts to Miller timing. We have late inlet valve closing LIVC, which is essentially the green line that you can see on the curve, where beyond bottom dead center, with the piston moving back up within the combustion chamber, we leave the inlet valve open for a bit longer than we would otherwise. The resultant effect of this is that some air-fuel mixture is pushed back out into the intake manifold. What this helps to do is lower our pumping losses, lower our compression ratio in the combustion chamber, but the sort of desired effect from that is that we are able to operate with lower engine emissions, typically in the region of 20 to 40% lower emissions than would have been the case on a similarly sized Otto Cycle engine. Our larger Type 6 engines utilise early inlet valve closing. So this is where the inlet valve closes prior to bottom dead centre, which means that the mixture within the combustion chamber is allowed to expand further, thus reducing its compression temperature and boost pressure. What this enables us to do is tweak our ignition timing, advance our ignition timing, and increase our compression ratio without approaching knock. And knocking is essentially an unplanned detonation within the combustion chamber where we haven't necessarily introduced the spark, or where the spark has been introduced, but rather the ignition hasn't occurred in the manner in which we would normally want it to. And what this enables us to do is improve our combustion efficiency, helps us to lower our exhaust temperature, which again has an impact to NOx emissions. However, the kind of one downside of EIVC is that we need to compensate the lower pressure in the combustion chamber with a higher pressure inlet intake mixture. Therefore, we need to compensate with higher pressure turbochargers. And just to sort of grammatically show this principle, this is essentially an image of the camshaft and the various cams along the camshaft. You can see the top left image shows the intake in green and exhaust in red, but similar profile geometries on the intake and the exhaust, rather. Apologies. The top right image shows us late inlet valve closing, and you can see that the inlet valve has a much more elongated cam profile, which helps hold the inlet valve open beyond where it would normally. And at the bottom of the screen, early inlet valve closing, again you can see a modified cam geometry with a much shorter cam on the inlet than on the exhaust. Moving on then to just discuss a little bit about GE's gas engines. Within the gas engine division there are two main companies, Jenbacher and Waukesha, and the combined sort of output of those is 24,000 or almost 25,000 megawatts of installed power capacity worldwide, and that's in the power range of 250 kilowatts up to 9.5 megawatts. Essentially, Jenbacher are a gas engine manufacturer first and foremost. They've been developing gas engines since 1957, and they, as I was saying earlier, their principle of combustion around how they've developed that gas engine is purely towards gas engines. So it's not a diesel-derived unit. There are considerable differences, as I suggested earlier, with regards to thermodynamic flows, metallurgy, and things like that that have been considered. So all of Jenbacher's business is essentially built around developing gas engine technology. And each of the engines within the product program is essentially built around three core competencies: so reliability, availability, and efficiency. GE have the intention of trying to be the most efficient engine on the market, the most durable engine on the market, and the most reliable engine on the market, which is where a very reputable service support provider, distributor network kind of comes into play. There are 5 core products within the product program, the smallest of which is the Type 2 engine, which is available only as an 8-cylinder inline set, with 2 outputs at 250 or 330 kilowatts electrical. It's a 1500 RPM engine, when operating in 50 Hz cycle, 1800 RPM if operating in 60 Hz cycle. The Type 3 engine then, which is really the workhorse of the fleet, the most engines delivered, it's been in the fleet longer than any of the others, is available from 500 kilowatts up to 1.1 megawatts. And really this is kind of the bread and butter of the non-natural gas applications. The Type 3 is a very durable, reliable engine, quite simple technology in regards to the gas engine, which is still considerably more complex than other types of engine on the marketplace. But this is really the engine that has been deployed across all of Europe and much further afield on more arduous gaseous fuel conditions, where there's varying gas quality, where there's varying gas constituents, such as in landfill applications, such as in wastewater treatment applications and things like that. The Type 4 engine then, which has a kind of a bit of a crossover in outputs, is available from 800 kilowatts up to 1.6 megawatts in 12, 16 and 20 cylinder variants. And the Type 4 essentially takes a lot of the durability and reliability concepts that have been developed over a number of years on Type 3 engines and matches those, with much more high efficiency technology. So the efficiencies on Type 4 tend to be a little bit higher than they are on Type 3. Moving through the product program to Type 6 then is where we get into the kind of the much larger scale. It's available from 1.6 megawatts to 4.5 megawatts in 12, 16, 20 and 24 cylinder variants. And the 24 cylinder version was the world's first 24 cylinder gas engine. It was also the first gas engine to use two-stage turbocharging. That was introduced into the product program, I believe 6 or 7 years ago now. The largest engine in the product program is the Type 9. The 920 is available only as a 20-cylinder variant and has an engine output ranging from 9.5 meg on 50 Hz cycles up to around 10.3 megawatts on 9.5 meg on 60 Hz cycles, ranging up to 10.5 on 50 Hz application. Excuse me. And sort of moving on then to engine control systems. Again, Jenbacher do things slightly different to a lot of other engines that are available on the marketplace. And there are three main controllers that are available on the engine system. The speed controller sort of takes care of the engine from a demand of call to run up to about 900 RPM and basically ensures that all systems are operational, ensures that lube oil temperatures are sufficient, the jacket water temperatures are sufficient, and that the engine can get up to speed prior to synchronization. You can see there during that first phase, the throttle valve is more or less completely open, the turbo bypass valve is more or less completely closed. We've then got that stage between around 900 RPM and 1500 RPM where the engine is essentially balancing itself and looking for voltage and frequency stability to be able to synchronize. And when we can start synchronizing, the throttle valve then opens, we're putting more fuel into the engine and we can bring the engine on load, so we start bringing the kilowatts up. At around 30% load, the Linox controller, which is the primary controller and patented GE controller, comes into operation and takes care of most engine functions during those normal operating procedures. And I'm going to talk a little bit more about the Linox controller shortly. But what you can see beyond around 60-70% load is that the throttle valve, which tends to be quite a large butterfly valve in a big bore gas line, fuel gas line, is more or less or completely open. The reason for that being, with the Linox controller active, we use the turbocharger bypass valve, the compressor bypass, to maintain output, to maintain efficiency, and to make the tweaks required to the amount of air-fuel mixture that reaches the engine in order to maintain emissions and maintain output. So essentially what the Linox controller is doing is moving away from a stoichiometric combustion to a lean burn combustion that is approaching the points where we might see misfire because the mixture doesn't have sufficient calorific value in it given the amount of air present. So we're trying to operate in quite a tight bandwidth that actually gives us our lowest emissions for the kind of best balance of efficiency. And what the Linox controller is doing is looking for the desired engine output from the engine considers the boost temperature of the mixture, the boost pressure of the mixture and the mixture temperature of the mixture and the air-fuel ratio to determine then the operating parameters of the engine at all set points between 30% load and 100% load to ensure that the engine maintains emissions, giving a sustainability of emissions between servicing and ensuring that all monitoring positions are in low pressure, low temperature environments, which adds to the kind of effectiveness and the ability of the engine to look after itself and ensure that it is delivering on the performance criteria that it is designed for. What I would like to do now is hand over to David Burke, who is going to talk to us a little bit about after-sales support, service and maintenance.
Thank you, Adam. Good afternoon, morning, evening, wherever you are, everybody. So just a little bit really about service, not quite as technical a topic, maybe not quite as complex a topic as some of the things that Adam has gone through. Mainly here I'm going to go through the principles around why is service important, more so than how specifically it is delivered in detail. But much of the essence of good service is around investment from either the company themselves, the customer themselves, or more usually through a service provider such as Clarke Energy, where we provide very comprehensive service on the Jenbacher engines as an option to our customers. But why is service important? Well, put simply, as Adam has already explained, feasibility studies are based on demands, but they're also based on an ability to operate, an ability to run a number of operating hours per year. And good maintenance, good service, good after-sales support is absolutely critical in ensuring that operating profile, the customer's optimal operating profile, is able to be delivered by the equipment. So really, from our perspective, one of the key pieces of advice to a customer considering a CHP scheme is that there is a significant level of due diligence that goes into how the maintenance, how the servicing of a prospective CHP unit is going to be delivered, who the customer chooses to partner with, and a number of key areas into which customers, we believe, should look in a great deal of detail to ensure that the performance, the availability, the reliability of their CHP unit is ultimately delivered. And that goes field service setup, training of technicians, engineers, and also the types of contracts that are available to customers to best suit their requirements and needs. So this is what we would consider to be the service life cycle of a CHP unit. It starts at the beginning there upon installation and project delivery with the commissioning of the unit. And Clarke Energy we have our own commissioning engineers. In fact, we have a dedicated team here in the UK of very experienced commissioning engineers to ensure that in the first step the engine is commissioned and the balance of plant as well is commissioned in its optimal state so that efficiencies are maximised, so that conditions such as ventilation systems, heat rejection systems, that all will inform the reliability and performance of the engine and the system as a whole going forward, are at their best and will be maintained through the life. I'll go on to touch in the next few slides around maintenance agreements and the field service and the part stockholding. Just on this slide, the other area that is critical is, as I said previously, the training of the staff who are delivering the maintenance provisions. So primarily this will be field service technicians, ensuring that they're fully conversant and fully up to speed with the latest developments of the technology, the type of engine, the balance of plant systems. And Clarke Energy, we have again an internal training facility that enables us to ensure that all of our internal technicians are up to speed. So moving now on to the kind of options that are available. So when a customer approaches a service provider, in some cases those customers may well be very inexperienced. It may be the first CHP scheme, it may be the first engine scheme that they've ever contemplated. It may well be, in fact, it's likely not to be core business for them. And so we set ourselves up, and other service providers also set themselves up to be able to provide a comprehensive maintenance agreement, one where all the services on the engines are covered, on the balance of plant is covered, so that the customer essentially can consider the CHP system as a black box, which is maintained in all respects, labour supply, parts supply for planned maintenance and for corrective maintenance, 24-hour breakdown call-out response in case of any issues, the supply and management of lubricating oil. All of those systems will be covered. We see in the CHP field that this is the kind of agreement, the kind of maintenance contract that is most often put in place between ourselves and CHP customers, just because of the nature of the type of applications that many of these engines go into. However, we do have some customers who have a little bit more experience, and therefore we're able to provide flexibility of kinds of contracts, and in some cases we supply exclusive parts contracts where we will supply purely authorised GE and Backer parts. So from our perspective, that will be another critical point of consideration for any customer, that whoever the customer is looking to partner with has supply of authorised original equipment manufacturer parts to ensure that the engines, that the balance of plant within the CHP scheme is continually kept up to the original specification with original manufacturer parts. And under those kinds of comprehensive maintenance agreements, I should have said, you will normally find an availability guarantee within those contracts that gives the customer reassurance that the feasibility study or the basis upon which the feasibility study is being done in the first place will be delivered by the contractor, and that the reliability and availability will be maintained high, so that the engines will deliver the savings that were originally conceived, or will have the best chance to do so. And that's certainly a standard feature of Clarke Energy comprehensive maintenance agreements. Another very important aspect of after-sales support, and becoming all the more so, is the ability for a selected maintenance contractor to remotely monitor and remotely support the plant, the CHP system, the engine, and the wider balance of plant. In our particular case, that means a system that's been introduced by GE in the last couple of years called MyPlant, which uses a broadband connection to the engines, to the plant on site, to continuously capture data. Essentially, all the data that is being monitored by the engine control system in situ is also then shared with a remote platform, a remote server, where it can be accessed at any time, where it can be represented in dashboard form to give a simple representation of performance of a fleet, particular engines which may have tripped and causes thereof, but also allows a further in-depth drilling down into more detailed information, looking at trends, alarms, temperatures, things that will see a progression of an engine, of a plant, whereby it may be possible to observe a particular issue and prevent it from leading to downtime and loss of availability and loss of savings before a trip actually occurs. So this is more and more critical. This is also beginning to move towards more condition-based maintenance approach, whereby analytics, real-time analytics, are being deployed to govern and to determine the way in which maintenance is delivered on an engine, such that it begins to predict issues and prevent downtime, as I already said, but also allows the stretching of some maintenance intervals to the benefit of the customer, reducing the need to switch engines off for planned maintenance and doing those interventions when they are actually necessary in accordance with observations on the engines. An extra very important aspect of remote monitoring is a much more simple one, and that is ensuring that if there is an issue on a unit, if there is an issue with a CHP plant, that issue is communicated at the earliest possible instance to the service provider. And in our case, we use a much more simple telephone-based auto dialer system, which in the event of an engine outage will immediately call a predefined number, which corresponds to on-call technicians, on-call engineers, who are immediately therefore notified of an issue with the plant and are able to respond either remotely through accessing the engine on a platform such as my plant, or equally attend site 24/7, whether the problem's in the middle of the night, on a weekend, Christmas Day, whatever. They get a quick notification and the ability to intervene and return an engine or a plant to service as quickly as possible. From our perspective, another critical aspect is the coverage that is able to be provided by a service provider. You see here a map of the United Kingdom. In this case, it shows locations of engines dotted around the UK, and it's very important from our perspective that there is an adequate number of field service technicians, engineers, whatever you would want to call them, to ensure coverage of the installed base of engines. So in our case, for example, in the UK, Clarke Energy has more than 70 field service engineers across the UK. We have an additional 10 engineers who have a dual commissioning and field service support function, and we have 20 or so workshop engineers who do more of the planned major service work. And from our perspective, it's very, very important that we have those numbers. We have that ability to both be close to individual sites to respond quickly in the event of any issues. We're able to attend site and carry out planned maintenance and corrective maintenance efficiently, and that we're able to deploy a quantity of engineers on call in out-of-hours periods, so that we have a critical mass of engineers, as it were, that enables us to put into place true 24/7 support for the engines that we are providing maintenance for, particularly under comprehensive maintenance agreements. Another critical aspect for support of CHP systems is a part stockholding. From our perspective, we would advise customers to be aware, or potential CHP customers to be aware, of what provisions their proposed partners have in place for part support, and in particular that those partners aren't solely relying upon part stockholding held by engine manufacturers. Clarke Energy, we hold very substantial part stock holdings directly ourselves around the world, in the region of £30 million worth worldwide across all of our territories. And this to us is a level of investment and commitment that is absolutely necessary for us to support and deliver the level of performance that we expect to deliver, and more importantly our customers expect to see on their units, in particular those units under comprehensive maintenance agreements. So we tailor our part stock holding in accordance with the types of engines we have in territory, the types of engines we have in a specific area, and even more down to the regional level, we equip our field service technicians, our engineers, with part stock holding that is specific to the type of engines they are supporting within the local area. So if we were to look across our van stock, across all of our field service technicians, it is not one uniform set of parts. It is tailored to the types of engines that those engineers are supporting within their locality. So another element is how is the major servicing carried out on the engine primarily, but also generator and other balance of plant. From our perspective on Jenbacher engines, as you'll see in the following slide, there's a service schedule that on a natural gas unit results in a minor overhaul, a top-end overhaul essentially, after around 30,000 operating hours, and a major overhaul, which is a top and bottom end, essentially refit of an engine at 60,000 hours. And those are by far the biggest planned service activities that occur in the maintenance cycle of the engines. And therefore they are very big in terms of contribution to the overall cost of maintenance. They're a large proportion of that. And they're also very important in terms of delivering uptime and availability, and specifically in the vents themselves, minimising downtime by being able to carry out these overhauls efficiently and minimising the amount of time for which the engine is switched off. From our perspective, we've equipped ourselves here in the UK to be able to carry out overhauls internally. As I mentioned already, we have a team of dedicated overhaul engineers who go out into the field to carry out minor overhauls in situ at the 30,000 operating hour point, and we have a workshop, a fully equipped workshop at our facility here in Knowsley near Liverpool, where we are able to carry out the major overhauls in situ on the engines, where we have equipment such as engine turntables that allow us to mount engines such that they're much more easy to access in terms of removal and refitting of parts and speed up the process of overhaul. But we also offer in a number of instances service exchange units such that we don't have to specifically take an engine in, overhaul the same unit and return it to site. We have an option there for customers to minimise the downtime caused by a planned overhaul, a planned major overhaul, by doing a service exchange facility and reducing, in many cases, the overhaul time by more than 50%. Final quick note from me, here's an example of the planned maintenance schedule on GE Jenbacher engine types. I'll just probably leave that there with you for a few seconds. As I already mentioned about the overhaul timings. Just as a point of clarification, some of the GE Jenbacher units are now beginning to move to an extended overhaul regime. The Type 3s already are at a 40,000 hour minor overhaul and an 80,000 hour major overhaul interval on natural gas, which is a potential benefit there in terms of life cycle maintenance and life cycle downtime. But that's giving you a picture of the plan of maintenance on GE Jenbacher units as an example of what a maintenance schedule looks like by engine time. At present, those planned maintenance activities are essentially driven by operating hours, but as already mentioned, with development of platforms such as my plant, there is a gradual move that we expect to see over the next decade or more, gradually moving more and more towards condition-based maintenance and the departure from strictly planned maintenance schedules such as this. But I'll hand you back across to Adam to carry on.
Thank you very much, Dave. The intention, everyone, was to go through a few project examples, and there are several reference sites that I intended to discuss. However, in the interest of time and getting the most from this session, I'm going to skip through these straight onto Jonathan's section, which is to discuss policy and regulation for CHP. And at that point, I would like to hand over to Jonathan.
Excellent. Thanks very much, Adam. My name is Jonathan Graham. I'm the head of policy at the Association for Decentralized Energy. And I'm going to talk a little bit about policy and regulation as it affects combined heat and power schemes. Just a quick mention of who we are. The ADE is a voice for a cost-effective, efficient, low-carbon, user-led energy system. And I think the focus for us is around that user-led, which is where CHP really comes to play. It's CHP is very much for us. It's a technology that requires a really deep understanding of the user's energy needs and how to meet those needs. Now, one of the things about CHP is that because it is focused on the user, there's a range of different policy and regulatory areas that impact energy users, and once an energy user also becomes a power producer, there's an additional number of areas that can come into play for that people need to be aware of. So what I'm going to do is I'm going to talk through some of them with a particular focus around carbon taxation policy, around other areas of tax policy, and some areas around emission and electricity regulations. I'm also going to just briefly talk about some areas of policy where there's a market value for CHP in providing power that users can actually receive payment for those. So won't take too long, and absolutely happy to take questions as we go or at the end. So do please feel free to chime in. Starting with carbon policies. So there's a range of different carbon policies that impact CHP, as well as I put at the end emissions regulations. Climate change levy, that's a tax on gas and electricity, which is delivered to non-domestic users. It aims to increase, and it always aimed to encourage energy efficiency, and that's going to actually be increasing by a not insignificant margin from 2019. The carbon price floor is a tax on fuel used for electricity generation, and that the whole purpose of that tax was to strengthen the EU ETS price. It's currently, the trajectory is frozen, so it's frozen at its current rate, but it might increase further in future. The carbon reduction commitment, that's a tax on all organizations using more than 6,000 megawatt hours electricity per year. That's ending in 2019 due to as part of a government-wide tax reform approach. The EU Emissions Trading Scheme is a European-wide cap-and-trade scheme where companies can trade emission allowances as needed. That applies to large-scale schemes. And then we've got emission regulations. So it's on carbon taxes alone. There's quite a lot there, and they all apply to different subsets of users. So some generators might be in the EU ETS and the carbon price floor and climate change levy and the carbon reduction commitment. Other smaller generators are probably just going to be captured by the climate change levy. So I think that's so it's important to kind of understand, based on the size, where you're going to get captured. For people that are under 2 megawatts, the climate change levy is really the area that matters. But once you get over 2 megawatts, you start to get captured by carbon price floor. And once you get over kind of 6 or 7 or 8 megawatts, you get captured by the EU ETS. So going on to the next slide, looking at kind of what policy is in place for gas CHP in terms of encouraging its investment. I mean, the government's long seen gas CHP as a benefit to the UK, both in terms of its economic benefits from a competitiveness angle and strengthening businesses and lowering their energy costs, but also on a carbon reduction piece to help us meet our climate change targets. So now there's a few areas of policy that what we in the association consider level playing field. So these are areas of relief that are provided to CHP generators, not because it's there to incentivize them, but they're just to keep them on an even playing field with other types of heat and power generation. One of those is a relief from carbon price support for fuel used for heat generation. So the government exempts all fuel that's used for heat from carbon price support. So carbon price support is designed just for fuel used for power. CHP obviously uses fuel for both. And that means that what the government has allowed is that fuel used for power can be or fuel used for heat rather can be exempted. CHP also receives an exemption from business rates. Power generation, big power plants receive favorable business rates treatment. So CHP receives its own version of that in terms of business rates exemption that applies to just the plant and generating plant and machinery. And if you're large enough to be captured into the EU ETS, there's a number of free allowances, especially essentially focused on your heat supply. Last on the list is embedded benefits, and this is a payment For exported power, that reflects your generator's avoidance of networks. On the transmission network, that's between 30 to 50 pounds per kilowatt of capacity per year, so it's quite substantial. It does depend very much on how much you generate at certain times. It also depends on where in the country you are, what level of value you get. Unfortunately, that particular value is currently in place, but its current proposals are on the table to reduce it from 2018, gradually reduce it between 2018 so that it falls to zero by 2020. So it's important to be aware of that. However, there are also distribution network benefits that are provided to CHP. And those distribution networks benefits will vary greatly from region to region, but the size of them is largely around that same 30 to 50 pound per kilowatt area. So those distribution networks benefits are sometimes missed, but they can be just as sizable. They too are dependent about whether you're able to run at the right times to support the network. So it very much something that needs a little closer look at as part of your pricing. I'm just going to have a quick check to make sure there are no, and see if there are any questions that. No. Okay. So then moving on to what we think of as more as incentives. CHP receives climate change levy relief on all its fuel. So if you had a boiler, you'd be expected to pay a £1.88 per megawatt hour tax on the gas. But CHP is exempt from CCL for its gas input. So that's a good benefit. The other one is that CHP gets relief from both the climate change levy and the carbon price support. So any electricity used by the CHP on site is exempt from the carbon price support, which has a price of about currently around £3.50 per megawatt hour. And then there's also a avoidance of the climate change levy, which is avoidance of about £5.50 per megawatt hour of electricity. So something to be taken into account when, again, doing your business case. Lastly, there's an incentive around enhanced capital allowances, which allow someone who's investing in CHP to access the enhanced capital allowance, and that allows the investor to write off 100% of the equipment costs against taxable profits in the year the equipment's purchased. And that tax benefit is particularly useful tends to be particularly useful for persuading finance directors. But if there's a profit to set it up against, then can provide good value in the same year of the investment. Now, I've talked about some of these incentives and some of these values and some of these level playing fields. All of these different values are dependent on the CHP receiving what's called CHP quality assurance minimum standards. I think you've heard it as well. Adam referred to it earlier in the day about the need to make sure when you're thinking about how to most optimally run your CHP that you're aware that if you run it inefficiently to, say, capture a power price and vent the heat, you might then lose points on your overall efficiency, and that might put your CHP quality assurance or CHP QA status at risk. Essentially, how the CHP QA works is that Europe sets and requires EU member states to only provide support and incentives to what they call good quality CHP electricity. And that's essentially electricity that comes from a CHP that is run very efficiently and captures its heat and uses that heat for a useful purpose. So the CHP QA determines the energy efficiency of a scheme, and that scheme is run by government. It uses something called a quality index score to determine the CHP's overall efficiency and how much fuel it saves. and that comparison is made against essentially what would have happened if you tried to generate that fuel, generate that same amount of heat and power separately, so in a power station and a boiler. And then it looks at what your CHP has done and says, well, how much energy have I saved by generating efficiently or generating in one process? And then we go put that through into the quality index score. So the CHP-QA requires the CHP to have electrical efficiency above 20%. And a QI score that exceeds 100, in the case of 105 for the proposed schemes. And then essentially as that QI score falls, because your efficiency isn't meeting the minimum standards, then the policy benefits are scaled back. It is a gradual element, but it does as your efficiency falls further, the benefits fall quicker. In the case of carbon taxes, these are reconciled at the end of the year. So if you're claiming release from carbon taxes based on the assumption that your CHP is efficient, then what can happen is that when you look back and say, and you look at your new CHP score, which looks at the previous year and how you ran, the HMRC will come and say that if there's a disagreement, if your CHP wasn't fully efficient, then you might have to pay some of the taxes back. CHP-QA values changed in January 2016. Grandfathering schemes was put in place, and those new values essentially provide a higher level of benefit for small generation schemes below 10 megawatts. So that's good in sort of recognition of their local benefits, efficiency benefits. There is generally accepted now is that the CHP scheme, while it does change every 4 to 5 years, that existing schemes are grandfathered in. So you can have some confidence. So the intention of government is that there's some confidence that the efficiency scheme won't change significantly on existing users after they made their investment. Just going to quickly move on to talk about local emission regulations. So larger industrial installations are subject to emission regulations regulated by the Environment Agency, but smaller installations are controlled by local authorities, planning authority. There is new European regulations under the something called the Medium Combustion Plant Directive, which is setting well before every different air quality from 2018 or 19, depending on when they implement the changes. There's going to be a whole raft of new requirements for any plant between 1 and 50 megawatt thermal input. So for electrical capacity, that's kind of 500 kilowatts up to 25 megawatts, very roughly. 250 kilowatts up to about 20 megawatts. So very roughly. And for NOx, which is the area kind of that tends to attract people's attention the most, it's going to be 250 milligrams threshold under that Medium Combustion Plant Directive. So something to be aware of, that is coming into force, and all planning authorities are going to be expected to meet that. However, something to be sort of aware of is that local authorities are open to setting their own standards. So something you do need to check whether your local area is setting its own requirements. So this is London. London is generally viewed as the leader here. So you can see on the right here that London set its NOx requirement for spark engines at about 150 milligrams. So that's something to be aware of. Other local authorities might set their own standards that might be somewhere higher than that, somewhere lower than that, but something to make sure that you're aware of before you start in the process. capacity market, just be aware there is a value opportunity for companies. The capacity market is a government scheme that is created to essentially make regular payments to people who can provide capacity when the system needs it. It can include electricity. Doesn't have to be responsive. You could be generating base load. As long as you are generating electricity either on-site or for export, when the system says that it needs to make sure you're on, then you're eligible for payment. So there is a penalty, supply for failure to deliver, but those penalties are never more than the payment you receive. The price is determined that you receive is determined through an auction. The auction occurs annually. There's an auction that happens for delivery 1 year in 1 year in the future, and there's an auction for delivery 4 years in the future. If you're a new build plant, you can actually secure a 15-year contract, so allows you to have that 15-year bankability of how much money you're going to get, which you can then use to back into your business case. The last 4 year ahead auction, which was held in December, had a price of £27 a kilowatt. So essentially a new build generator was able to get a £27 a kilowatt value, which they were then able to secure for the full 15-year term of their investment. When the 15-year ends, you can go back into a new auction on a 1 year basis, if assuming the mechanism is still in place. Generators and users who say, well, that sounds like a good value, but I don't know how to do it, or the regulations are quite heavy. I'm not sure how I participate, or I don't particularly want to get too involved in that. You can participate through aggregators. So a number of companies in the marketplace, either suppliers or aggregators, who will take a commission or a cut, but allow you to receive an element of that value without having to get stuck into the regulations. Another area of value for people who for CHP generators that are investing is in National Grid balancing services. So there's a range of different balancing services that National Grid provides. There's essentially something called STORE, which is where National Grid will sort of, in a similar way, will suddenly need, with 20 minutes notice, will know that ask that you become available if you weren't already, and provide a payment for that. There's also a number of what are called sort of more fast responses, where National Grid needs things to help them keep the system in balance. Some of them are, in the case of frequency response, less than 30 seconds. All of these have a value and can be dealt with. You can secure contracts in National Grid to provide these values either directly or through an aggregator. All of them also require different. It's very user specific about whether the user is able to provide that kind of flexibility, whether the site is able to manage that flexibility. There will obviously be knock-on effects on O&M costs that have to be factored in. But National Grid's balancing costs and therefore the payments that it's making to generators for balancing is expected to double over the next few years. As increasing amount of intermittent wind and solar comes onto the system. So the value stream for generators is expected to be much, much greater. It's hard at the minute to bank these values when you're building a business case, but so they're essentially viewed as upside once the unit's built. But it's about, from our perspective, ensuring that if you do want to, ensuring that you're aware that these values exist, so that you can put those design parameters into the kit before you build it, so that you can access them after the fact. So that's it from me on policy and regulation. Thanks very much, everyone. And I'll just have a quick look. I haven't seen any questions, so hopefully everyone's happy. If there's anyone who wants to throw in a question or anything, just please do throw it in.
Thank you, Jonathan. And yes, to all sort of parties involved, many thanks for taking time out of your busy work schedules to participate in the webinar. It's very difficult over a short period of time in the space of just over an hour to provide a thorough appraisal of CHP. Although I do hope that you have found the talk to be both informative and useful. I'd also like to take the time to thank both David and Jonathan for contributing with the speaking, which gave my voice a little bit of a rest. If you have got any questions, please do fire them into the forum. We are taking a look. I've got a few that will sort of kick us off, and equally, if we don't answer all of your questions kind of live right now, we will follow up to all questions via email and possibly via telephone conversation as well, should that follow. So looking at, I've got three kind of initial questions. The first of which asks, what improvement in reliability and availability can be offered whilst utilising sort of the online monitoring software such as MyPlant? So David, if I can hand that one over to you, please.
Yeah, no problem. So from our perspective, Clarke Energy, we've had a system that covers the basic ground of what the new GE MyPlant system covers for many years. It was essential for us to be able to deliver comprehensive maintenance agreements. So that's really about the data capture, the high-level data capture, the operating hours, the power generated, and those kind of characteristics, and whether an engine is running or not running at that moment in time. So we've had a system that covered those bases for a few years. MyPlant, as I mentioned, is pretty new. It's been released as a commercial product in the last 1 to 2 years. It does have these analytics being developed, but to be perfectly honest, at this stage, they're not. They are working towards, as I say, condition-based maintenance at a later time, and a gradual program of works. And it's an exciting program, and it's one we're completely behind. At the moment, those analytics, those real-time analytics, are not so well developed to be a game changer around delivering engine availability performance. Once they start being able to do condition-based maintenance such that we can change and depart from planned maintenance schedules, and once they are truly predicting trips and outages, then that might be a different thing. But right now, it's in the development of those analytics. It's still fairly early and isn't really changing the scenario around availability delivery. I mean, we are regularly delivering availabilities of 95%, 97, 6, 7, 98%, some engines 99% availability. So those levels are very high, and MyPlant's not so far developed yet in those analytics to change that materially.
Thank you, David. Okay, another question that we've had, Jonathan, which I think will be most suited to yourself. Are there any sort of concerns or thoughts from the association regarding how, obviously, Article 50 and Brexit might affect the energy mix, affect incentives, and affect the industry as a whole in the coming years?
Yeah, I don't think we see Brexit and Article 50 having a big effect on the CHP sector and the opportunities for CHP. The CHP we see as an investment against uncertainty to a certain extent, and the uncertainty about electricity prices and energy costs. Brexit will impact the ability for larger generators to sell power across different across internationally, but for smaller generators, the CHP generators tend to be we don't see that as big an issue. And also, I think important thing is from our perspective, the UK government sees CHP as a positive part of the energy ecosystem. So leaving Europe, we don't think will have an impact there. Maybe the things that obviously investors' confidence in these sort of things will obviously have a knock-on effect on the ability to make big capex expenditures might are obviously kind of something that people will be thinking more cognizant of in this period, but there's nothing on from a policy or regulatory front that gives us any pause to concern.
Thank you, Jonathan. And that almost sort of goes some way to answering another question that we've received, which is with regard to market trends, growth forecasts within the UK. And as you're alluding to there, you know, government are still seen to be supporting CHP as a company. Certainly, we at Clarke Energy are continuing to see a very high demand in combined heat and power products and trigeneration opportunities and schemes of the like. And as you say, the economic conditions, certainly here in the United Kingdom, are very favourable at present for CHP. Another question that we have received relates to generation voltages and what the preference would be, or where the kind of the cut-off might be for moving from a low voltage generator, maybe a 400 volt generator, up to a medium voltage generator at 11 kV, with a kind of follow-on to that question of, is there a subsequent impact to maintenance, and are there any regulatory conditions or impacts that we need to consider? So I'll handle the first half of that question, and perhaps David can take a look at the second half. With regards to generation voltage, it is very much site-specific. You know, you may have a central 11 kV ring. You may have only have a sort of a dedicated 400 volt low voltage bus bar. So an analysis needs to be made on a site-specific basis. Where we find the generation efficiency of the generator, of the alternator, kind of comes more into the favour of medium voltage, would be around the 1.5 megawatts mark. So below that, invariably you would look to install a 400 volt generator, and then if you need to connect onto an 11 kV system, you would step up via a transformer. And the reason for that is because of the generation efficiency of that alternator plus the transformer loss still equals a higher generator efficiency than on a larger generator. Above 1.5 megawatts, invariably you would look to generate at medium voltage or high voltage in the first instance, because it becomes more economically viable to do so, more technically viable to do so. On the maintenance side, I'll hand over to David for his thoughts.
Yeah, so on the maintenance side, there'll be different regulations typically from country to country. In the UK, for example, we have to have kind of medium voltage HV authorised people to carry out any work. So that's part of the training that we ensure that we have covered with our service engineers. Some very, very strict and clearly written policies around how to work on any equipment, both LV and HV medium voltage, any electrical systems, but clearly even more onus on the medium voltage, high voltage equipment. And it also kind of feeds into it is probably one part of that due diligence that a customer should be doing around a service provider, that level of training is in place, that level of accreditation is in place from the company you're looking to work with, to ensure that they can actually carry out the work efficiently, that they have enough trained people, so that an issue with some switchgear or a generator isn't going to cause an extended downtime just because of lack of personnel. And it's a wider point then into things such as gas supply, where all engineers in the UK at least working on the natural gas CHP system under regulation need to have a gas safe accreditation essentially. So there's a number of different training and accreditation issues to be aware of and questions to ask potential suppliers and potential service suppliers around their capabilities.
Thank you, David. Another question that has come in is, can CHP be viable for companies if there isn't a large on-site demand for heat? And again, this really comes down to the economic situation on a particular site and whether the spark gap is sufficient to justify generation only. As Jonathan was discussing, there are other financial mechanisms in the form of the capacity market that exist here in the United Kingdom that haven't existed in the past, which helps the business case for a generation solution. However, you may forego some of the other kind of regulatory or incentive benefits if your CHP quality assurance score is insufficient to break that magic 100 number. So if you don't have a sufficient on-site heat demand, it may still be worth considering on-site generation, because there could still be a financial case for it, albeit the financial case may be somewhat diminished. Equally, however, there may be an external consumer for your heat generated. So it may well be worth investigating the concept of a district heating network and actually selling heat to other local users. So it's still worth exploring, certainly. Another question that we have received is a very good question, actually, very pertinent given changing emissions circumstances around Europe. So will new build Jenbacher units meet tight emission standards, such as in the GLA, Greater London Authority, out of the box, or do they need extra kits to achieve these levels? So as Jonathan was describing, we are kind of under the current changes right now to move to the medium combustion plant directive, which at 5% reference O2 level, which is the kind of the standard O2 level that most manufacturers refer their emissions to, we need to achieve an NOx emission of 250 milligrams NOx. All new Jenbacher engines, absolutely out of the box, will achieve the requirements of MCPD. That said, the GLA, Greater London Authority, have been seen to be requiring much lower emissions levels, and the question does actually refer to 150 milligrams per normal meter cube, but we've seen far lower levels than that in the Greater London area.
And this is with regard, that drive is about existing high background NOx levels in London in particular.
Thanks, Dave. Yeah, so in London, what we are seeing is a tendency, I won't say to penalise, but I will kind of say to penalise CHP technology for their NOx contribution, because there are very high levels, and this is true of other cities across the United Kingdom and across the world, actually. So for those kind of applications where we're having to almost achieve kind of 90% reduction in the baseline NOx levels from the engine, all manufacturers will need to consider additional technology, and that normally takes the form of selective catalytic reduction. So in a similar form to the greenhouse applications, where we're scrubbing our exhaust gases to produce a clean CO2 and water vapour, we would use a selective catalyst and urea injection into the exhaust stream to help reduce NOx emissions in those kind of applications.
There are some small engine options with rich burn or stoichiometric burn engines that have a simpler way of reducing NOx emissions down to some levels below 250. But the problem with those kind of technologies really is they're not a viable alternative to a lean burn gas engine such as the Jenbacher, because their electrical efficiency is significantly lower, and therefore the typical savings they will tend to generate are much reduced. So there's a little bit of a compromise, maybe not the right word, but going on between efficiency and emissions, and as Adam says, the selective catalytic reduction kind of system, the additional plant on the engine exhaust is the best means to retain both efficiency of operation of a lean burn engine and comply with some of these very low NOx emission levels.
Thank you, David. We have actually received another couple of questions, both relating to emissions and network operation versus island mode operation, so grid parallel operation versus island operation, how the Linux controller sort of manages the situation between those. What I would like to do with both of those questions actually is revert via email, if I may. So apologies if we're not answering your question directly over the webinar, but we will follow up very quickly on that. It's just a slightly more technical response that probably is not best fielded in this forum. At the end of the session, when we sort of say our goodbyes, Users will be redirected to a very short survey provided by the operator of the webinar, just to provide feedback. So please do provide some feedback with regards to call quality, with regards to speakers, our knowledge or lack thereof, and the general overall service that you have sort of witnessed with regards to the webinar. We do appreciate any feedback that you can provide. I don't think we've had any new questions. So as I say, those who have asked queries that we've not answered, we will get back to you very, very shortly. And on that note, I would like to again take a moment to thank both Jonathan and David for joining me during the webinar, and thank you all for your attention over the last hour and a half. Thank you and goodbye.